nanohub.org.
Online simulation and more for nanotechnology.
Okay, so first of all, welcome back to everybody who's here. And what I'm going to talk about today is all about optical amplifiers. And I'm going to just show you briefly an example of like actual optical amplifier. This is something you can buy off the shelf. And something that's interesting is like this Erbium-Doped fiber amplifier. So it's like one of the specific types of hardware. And it's actually marked with like one of these like laser safety things. So theoretically it's not a laser, but it does have certainly some overlap with the laser. So that's probably why. And you can also see it connects to like a Ethernet type cable as well. So it's kind of like in some ways interface between electronics and optics. So I'll start with talking about some of the principles of optical amplifiers. Okay, so just to recap what they are in general, remember we said last time that you need an amplifier beyond a certain distance to boost the light. And so basically the two types of amplifiers we talked about, first we said regenerators, where you basically collect the signal and then convert it to electricity, and then take that electricity, convert it back to optics. We said that can be done, but it's like really slow after a while, and you may have to do that many times. And the other way that's more direct is just to directly amplify the signal based on the signal you already have, okay? And so in either case, obviously you have to do it every so often, like every distance L. Although the L depends, of course, on the wavelength and the fiber that you're using and so on and so forth. Okay, so basically the principle of the optical amplifiers is related to that of lasers in the following sense. So in lasers, we said you have both spontaneous emission and stimulated emission. But the key difference is that they both have a certain rate, but the rate of stimulated emission can be tuned by kind of the photon density and the level of population inversion, right? So if you have high population inversion, high photon density, you have lots of stimulated emission. If you have relatively low photon density, then you mainly have spontaneous emission. Okay, so if you want a laser to work well, you want to have stimulated emission dominate. So that means high population inversion and high photon density. The concept of spontaneous emission suppression should still be used in an SOA, like a semiconductor optical amplifier or other type of like pure analog type device. And of course, you can kind of see visually like why that's the case. So if you have a single photon coming in to the semiconductor, it has a certain frequency, has a certain direction. You want to clone that photon, right? Because you're trying to amplify a given signal. And so if you clone a photon that has different properties, then that's not very useful. Or if you create random photons from spontaneous emission, that's also not helpful, right? Because now you are degrading or even entirely losing your signal with spontaneous emission. So that's why stimulated emission is so critical in the optical amplifiers. Okay, so as I mentioned, the key thing that we need in the optical amplifiers is to focus on stimulated emission. And so to get basically something that's dominated by stimulated emission, we're going to have something that's like the reverse of Beer's law. So instead of absorption, we said stimulated emission is kind of its reverse. And that's when you have population inversion. So instead of having dP/dZ is minus alpha p, where p is the obviously the power, z is the distance along the optical amplifier, and then alpha was the loss. Now you have a positive coefficient g, which is your gain coefficient. And that means that if it's a length L and you solve this equation, then you get this exponential growth in the output power at a distance L along the length So basically, P out is Pn times e to the GL, okay? And of course, the difference that's very important compared to lasers is that there's a lack of feedback. Okay, so the reason why that's important is, of course, A, makes it different from lasers, and then B means that the amplification can be as broadband as your gain. So that actually is a good thing in this context, because oftentimes, whatever signal is coming in, it could be multi-wavelength, and you want to amplify all those wavelengths instead of just one wavelength. Whereas with a laser, you may just want to emit a single wavelength at a time. So this is kind of a different concept. So it's broader band, but then the sacrifice you make is that it won't necessarily be as strong in amplification because you only get basically one shot. Like this e to the GL is your only chance to amplify. After that, obviously, it can amplify. So basically the idea is light comes in with a certain Pn, comes out at Pn times e to the GL. So the key thing here is that if you have many of these links, and then every time you have like a gain of e to the GL, and that means that you should basically have e to the GL equal to the loss along each of these links between individual amplifiers, right? And so in other words, this is going to maintain kind of like equilibrium. So you'll have like a gradual decay as you travel down the fiber, and then you'll have a boost, and then you'll have a gradual decay. But the overall pattern will be basically periodic over like all these links. And so you can just keep it going as long as you want, right? So that's really the most critical concept. Now, there are some complications, of course. One is basically gain saturation. So in other words, if you have like tremendously high amount of input power, you also can try to amplify it, but the gain factor may not be as large. And so what this is showing is basically there's oftentimes like a so-called saturation power, P sub s. And if your power is on the order of or greater than P sub s, then you're very likely to see a degradation in the amount of gain. And so it's not necessarily flipping sign, but it could be reduced a factor of 2, factor of 4, or more, depending on how close you are to P over PS. So if P over PS is 1, you can see there's factor 2. P over PS is 3. So it's 3 times the saturation. Now you have a factor of 4 degradation, and obviously it keeps going down. So then that just tells you that, sorry, I need to fix this slide actually, but that it should be degraded by, this 1 over P plus PS. So this actually creates like an implicit equation. And so this actually tells you that if the amplifier is very long, especially, the amplification won't be quite like this full e to the GL, but it's going to be degraded compared to that. Now, just in case you're wondering, like, when does this PS kick in, basically? So actually it can happen at relatively modest powers for a lot of these sources, optical amplifiers. So this just showing an example of about communication. I mean, this is pretty old in some sense. Like this is just over 1 micron wavelength, so this is not like very commonly used system. But it's just showing that, basically for sources that are, powers on the order of maybe like 0.18 to 0.91 watts with basically different levels of pump power that are propagating over 1.3 kilometer link. There's basically a linear amplification factor as a function of pump power. But as the pump power becomes like larger, like on the order of 1 watt or greater, you see that the amplification factor starts bending over. And keep in mind that this is a log scale. So, if there's any bending at all, that's actually a big change in the absolute ratio between the kind of the linear expectation, or I should say, well, technically it's linear in the log plot, so it's exponential, and then this sublinear slope in the log plot, which is associated with the saturation. And so this closely matches the correct theoretical equation, which I didn't show you, but I'll fix that soon. Okay. And then another challenge, of course, is noise. So these devices, optical amplifiers, are likely to experience significant noise. And so basically the noise is dependent on gain, of course. So if you have no gain, basically you're not introducing any extra noise, but basically this G-1 factor tells you bigger the gain, bigger the noise amplification. And then this N2 over N factor, basically it's like a measure of the the fraction of population inversion. So as this goes to 1, of course, you get more noise. And there's a proportionality to the frequency, right? This H nu factor. And then if you basically try to divide the signal by this noise factor, now you actually get something like, because there's also amplification of the signal, of course, then you get basically signal noise ratio actually overall does improve, okay, with gain. So in net, it's not necessarily a bad thing, but you have this G-1 factor. So then that means that the net gain from G over G-1 is not great at really high Gs. And you also have this degradation of delta F, like basically the frequency bandwidth. So then that means that even in kind of like the most ideal case, that you usually get a slight degradation in the signal to noise ratio. And of course, if you had a very noisy amplifier, so for example, it had a lot of spontaneous emission, or like there were just some crosstalk issues or something else was happening, then it could be more than 3 dB. So then that means that you need to play some additional tricks if there are like a tremendous number of these links in order to keep the noise to manageable levels, right? So of course, this was like this simplified case in some sense. I mean, there are ways to manage this noise, obviously, but this is just showing you that if you don't really do anything to manage the noise, it can become a problem over time, like it keeps getting amplified. Okay, so now discussion. So first question is, did you get all of that? So just go back to here for a minute. So basically the key thing here was just saying that the optical amplifiers increase the input power exponentially with the length, except for saturation effects. But you only get one pass, unlike a laser. So there's no feedback. So they can do broadband, but they cannot do really, really high amplification factors usually. So that's the trade-off. But if you have an optical network and you have like several of these things, then you can basically have like your signal is here, like this is your source, and have exponential decay over the length of this link, L, and then you can have a boost from this gain factor from the SOA. And then it can go back to basically the original power. Now you can boost it again. So it basically becomes like kind of this almost sawtooth type pattern repeated over the whole like optical network. So that's what allows you to keep going across the Atlantic or Pacific or something, even in the presence of potentially significant loss. Yeah, it's repeating the whole signal, exactly. So that's like why in this context here, like this element, I only showed one here, but it could be like actually many of these things if you have a long enough distance. And so it's all determined by this length L, basically. How far can you basically degrade the power before it becomes hard to detect and you get like really bad signal to noise ratio? So you're trying to avoid that, obviously. And like I said, you are introducing a little bit of extra noise by doing this, but it's probably much more manageable than a lot of other strategies here. And I think that when I talk about the hardware, I'll try to explain in a little more detail about this. But I guess the question is like, Was anything unclear, or do you have any questions? Yeah. Okay. Okay, so then without further ado, I will now continue with the optical amplifier hardware discussion. And basically there's going to be two types of hardware that I'll be focusing on. The first are basically like Raman amplifiers, and then the second would be Erbium-Doped fiber amplifiers. So then that's basically what's depicted here, the latter. Okay, so what is a Raman amplifier? So simply speaking, it's a mechanism where you can have a pump frequency that will boost a signal. Okay, so then in other words, you have some signal coming in, and you have this pump frequency, and this pump frequency interacts with the signal to amplify it to a significant extent. And then it basically can then come out as like your new signal. Okay, so this is like a, something that's based on the Raman effect, right? And so basically what's happening is that the presence of this signal is causing the pump power to preferentially be shifted into the signal to basically boost the signal in a way that's coherent with respect to the original signal. So you maintain the polarization and the wavelength and everything else of the original signal. It's not just like random noise at this point, right? And if you don't have that signal, then you don't get that pump. So this is because it's nonlinear effect, and so the nonlinearity depends on your original pump and source frequency. So if you're missing either one of those pieces, then you don't get this nonlinear interaction. And that was something that I showed in the first week, like a while ago. So without going into all the details of that again, just remember that you get a coherent amplification of your signal from the pump. And this just showing the level structure that's associated with the signal and the pump frequency. So usually the pump frequency is a little bit higher than the signal frequency, right? And so just to give you a rough idea of like kind of what the bandwidth is, it's determined by the vibrational spectrum of your material, right? So it can actually depend slightly on exactly like what kind of material you're dealing with. I believe this example of Raman gain was for silicon oxide, like quartz, basically. So what this showing is that if you look at like what the signal output as a function of the original frequency minus some frequency shift, okay, you can see that actually the probability of emitting a signal at the pump frequency exactly is actually very low. But as you go to slightly lower values, then it becomes like much higher. And so you get like a much larger gain factor, here called the Raman gain. And that actually is very broad band because it goes from basically 0 up to about 40 terahertz. And just for comparison now, remember 1.55 micron light is around 200 terahertz. So the bandwidth is close to about 20% of the frequency. So that's pretty wide. But you can see also that there's a much narrower peak range right here. So of course, if you're trying to amplify this 1 micron wavelength, then you would probably want to be mainly in this region, right? But of course, as you know, nowadays we're not really using 1 micron, we're closer to 1.55 micron. So you'd want to, if you wanted to design like a modern Raman amplifier, you'd want to take your 1.55 micron frequency, about 200, and then you'd want to probably subtract maybe about 12, you'd add 12 to the pump so that your output would be 212 minus 12, or 200 terahertz. So you'd be pumping at 212 terahertz. And I don't remember the exact value of that, but it's probably around 1.5 microns, right? So it's just a little bit shorter wavelength than the output you want, right? And so this here, basically this is 1.5, that's 1.55. And of course, this is exaggerated, this gap between vibrational states and the ground state. But it's all very material dependent, so you could have another material that has bigger gap, another material with smaller band gap. And I certainly wouldn't expect everybody to memorize like what all the gaps are for different materials. That's not the point of the class. But just to give you an idea that that happens. Another thing that's important about Raman amplifiers, of course, is just like we said in general, they also experience saturation. So this is just showing kind of a simple example of how much saturation can occur in these various parameter regimes. And so this is actually, I think, supposed to be the saturation parameter for the gain divided by the actual gain. And then this is the gain parameter, G sub A. Right, and so basically it's just showing that as you go to higher gains, you have more saturation occurring, right? And so there's less overall amplification in the presence of relatively high gain factors, right? And then if you look at the spectrum, just to kind of like put this into more modern context, I mean, you could potentially have like, a pump, maybe kind of like around 1.5 microns, and then it can actually amplify this whole range from about 1520 to 1620 nanometers. And that's actually more than wide enough for any like wavelength division multiplexing type approach, right? So that just shows you that in principle, this can actually work pretty well. And showing the gain here was like on the order of 10.5 dB, so more than order of magnitude. So that's enough to make up for like some significant losses in the system, right? So the second type of hardware I want to talk about is the erbium-doped fiber amplifier. Okay, so there is a difference between the previous case and the EDFA. Okay, and the key difference is that EDFA is more like an atomic transition, whereas the other thing is like you have like kind of like a blurry range of levels, but here it's like very sharp levels, right? And to be honest with you, this diagram may not even do it justice because it looks like it's much wider than it really is. I mean, these are all very sharp transitions. They're widened slightly by the type of matrix they're embedded in. For example, if they're embedded in glass, it's probably wider than a single crystal, but it's definitely a very narrow transition overall. And so what you see here is that if you consider this state here, which is labeled as 4i 5/2, to be the ground state, you actually have several ways to excite and then de-excite the system. So in particular, you have two options for pumping the system. So you can either pump it optically around 0.98 microns. So basically go from the 4i 5/2 to 4i 1/2 state. And then you can basically have like a non-radiative transition down to here. Or you can actually pump at a wavelength that's just slightly shorter than the output wavelength that you're targeting. So basically excited at 1.48 microns, and then it's just wide enough. It has about 0.05 micron width so that you can actually now go down to the bottom of this range of energies and then re-emit at about 1.53 microns. And so the nice thing there is like your pump is not too far away from your emission, but it is separated enough so there's not like really any crosstalk between your pump and all the emission wavelengths, which are the ones you really want to amplify. And so this actually is showing like what is the absorption profile here as a function of wavelength versus like what is the gain profile that results from the same material. And so the key takeaway here is that if you preferentially pump like right around here, then you have like a pretty strong contrast between the absorption and the gain. So you're not really going to amplify any like, stray light or whatever at 1.48 microns, but you still will have like very good gain in this region. And so now you can actually see why we're so interested oftentimes in wavelengths like 1.53 or 1.55 microns, because those match the peaks of the gain of this erbium-doped fiber amplifier. So that shows you that this is very appealing, like in terms of getting like very high gain values. And then the additional advantage of 1.55 is just it's separated further from 1.48, so that further reduces crosstalk. You had a question?
So are these more
common? Yeah, I would say nowadays these are very common. Like essentially the most number one choice for most of these applications.
Yeah, it just sounds better. It's like, oh, why do people use the other one at all then?
Well, I think that actually the Raman work was first, historically. Well, they have to check. At least I think that Raman amplifiers were kind of the first thing that people are using. And then they obviously came up with the erbium-doped fiber amplifier technology, and then it's become very successful. So I would say it's dominant share of like, especially these long haul telecommunication markets. But I do think that there are some labs that are still experimenting with Raman physics, and actually there have been some, slightly off the beaten path applications of Raman, such as using Raman for like silicon lasers. I think Intel was working on that a few years ago. So Raman can still do some interesting stuff. And there's a lot of interest in silicon lasers, especially because then you can make a single silicon chip that has both processing and like optoelectronics for telecom and other applications, and maybe even sensing, like optical sensing, right? So that was like a big source of excitement, but I'm not sure if they're still pursuing that, although I don't have special insight into Intel's corporate strategy. So it's possible. So anyway, so what does the gain look like for these EDFAs? So this just showing here that if you look at the gain versus the length of the fiber, that of course, as you would expect, the gain keeps going up for longer and longer lengths of the fiber. But one thing you notice actually is that if you have very moderate pump powers, and keep in mind this is milliwatts, so if you're like below 1 milliwatt, for example, it's actually better that it's short. But do you know why? Why would it be better? If it's really short, that it's a shorter length, or very low power, why would you want a shorter length? Well, so I think the main reason is that it's hard to get the whole fiber into like a good population inversion state, because now you're like pumping it really weakly. So then if you have a long fiber, then it takes more power to basically reach population inversion. And so then that's why, like, as you go, to higher pump powers, then you see that basically the 5 meter length actually turns on first. It turns on well below 1. And then the 10 meter fiber turns on just below 1, 15 right at 1, and then 20 just above 1 milliwatt, right? So it's kind of proportional to the length of the fiber, more or less. So I thought that was interesting. And then if you want to see like kind of broken down more discretely, then this showing you for this 1 milliwatt fiber that actually this amplifier length, once you reach a certain threshold, you're getting out of population inversion, and actually it goes below 0 and starts becoming negative. So then that means that it's basically becoming a good absorber of your source. Because your source, remember, can also be absorbed if you go back to this graph. So if your signal is like 1.55, keep in mind it still overlaps with this absorption. So if you're not in population inversion, now it's absorbing your signal. So you have a minus 10 dB gain. So that's actually a very critical design choice for EDFAs. Like you have to not only choose the right material, of course, by choosing this, but also make sure that the length and the pump power is commensurate with getting like the appropriate amount of gain. And definitely don't get into this regime here, because basically once you're in this regime, then it's doing the opposite of what you want. So that's really bad. And you can see that as you go to higher pump powers, it's still possible to pick a length that's so long that it'll actually not be able to reach population inversion. So there's always a length that's bad. And the reason why I'm warning about long lengths is you might think it's like crazy to have like, say, 50 meters of this EDFA. But the point is that usually when you get these, it's not, you don't get like just a 50-meter long thing, like, but it's like rolled into like a, you know, basically wrapped around some sort of spool or something, right? And so then you could have something that's very small, handheld, but it's like hundreds of meters of fiber. And I know that some people at Purdue will do experiments on kilometer long fibers in the lab, right? And obviously they're not like laying a fiber across the whole campus, but they're just, you know, working with that spool of fiber, like basically more or less as is, maybe pulling out like the ends on both sides of the spool. So then that means that you have to be attentive to that issue if you're designing this. But if you do this correctly, obviously, you know, you pick the right length and also the right amount of pump power. Now you can actually get gains that are well above the 10 dB that I was showing you earlier for Raman. So you can get up to like 30 or 40 dB pretty easily, which is very substantial. So then the practical advantage for building out a whole network is that now you know, you're concentrating the gain in specific wavelengths that you really want, first of all. But then second, because the gain is so much higher, now you can do two things, like reduce the amount of extra noise that's being introduced into the system, because like you have less of these amplifiers, and then you can just save money on just building less amplifiers in general. Like you just propagate down the fiber for much longer distance before you have to boost it, right? Because before with the Raman, like we're only boosting about 10 dB, so you might have to go like this basically to keep it going. But now you have like four times less because you have like so much more gain. So that's a big advantage. And of course, I don't think 40 is really like a theoretical upper limit or something, but that's just like kind of what was shown for kind of this more practical case of up to about 10 milliwatts. But certainly I think you could, you know, if you pick a long enough fiber and a higher pump power and so on, you can easily get, you know, something on the order of 100 dB gain. I don't know if anybody really tries to go that far, because I think the issue is that if you had 100 dB loss before you try to basically amplify it, then there's some concern about like basically spontaneous emission or other factors basically degrading the signal to noise too much. So you have to find like a sweet spot where you get like, you know, essentially very high gain, but not so high that you're compromising signal to noise. So it's all a trade-off in some sense. And now if we look at like what the noise figure is for these kind of systems, then you can see that it can potentially increase a little bit as you go to longer amplifier lengths if you're not careful. So I think the real point of this is just that in the best case, though, if you design this correctly, you can actually keep the noise figure associated with the EDFA close to kind of the theoretical limit around 3 dB of additional noise or signal to noise ratio loss. And then if you compare that to the gain, you can see this factor here. So when we chose, I think this was input power was like 10 milliwatts or whatever, then you can see that you can get like very high gains. Like if the amplifier length is long enough, like close to 100 meters. So what this is actually indicating is that if you have a high enough power that's reaching the fiber, the EDFA, in the first place, you can basically limit that signal to noise ratio issue very substantially. But if you don't, and you're basically putting too low of a power into the system, especially over long amplifier lengths, things like amplified spontaneous emission and absorption start coming into play. And so you actually get into this negative gain regime or absorption regime. So the key thing is you need to have enough pump power, you need to have enough inserted data power, essentially, and then you need to ensure that basically the extra noise that's being introduced into the system is close to the theoretical limits. So then in terms of the real implementations of the system, I mean, this is just showing some practical examples, right? So this might be a system where you have some sort of probe, basically to insert information into the system. In this case, I think you've already basically converted your signal into light, right? So by the time you get here, you're in the fiber and you're basically just sending some test signal into the EDFA. EDFA, of course, has several different components. So here, the pump is actually happening at 980 nanometers. Remember, we said that's one of the pump wavelengths. And then it's going through basically a filter, and there are actually two filter steps. So this is like a ring resonator filter, and then there's a long period grading filter. And so the idea of the long period grading filter is just to filter out any wavelengths that are outside the specified range. And of course, that in a lot of instrumentation, that's very critical, not to insert unwanted wavelengths and then have unexpected nonlinear optical effects or the like. And then you can also see that there's another pump that's actually at 1480 nanometers in this system. So it's actually using two laser diodes in tandem to basically get like a higher level of total amplification from basically this 14 meters of erbium-doped fiber amplifier and then this 15 meters. So you can see the total length in this particular instance was like on the order of 30 meters, which is enough to obviously get gains exceeding 30 dB, right? So that's pretty substantial. And then this also showing that you can actually sometimes have basically just a very similar type of system, but then couple in two 1.48 micron laser diodes into the system, kind of in tandem with each other in a single unit. And I think the idea here is just to maximize the gain compared to the other system I showed you where there was just one of each type of diode, right? So, I mean, obviously both work. And here it's just showing the optical isolator more schematically. I mean, but basically the optical isolator is really a filter just to filter out unwanted wavelengths. You're not really doing that much else since the fiber takes care of like filtering polarization and a few other factors usually. Okay, so in terms of using these in systems, okay, so this actually is intended to show what kind of filters are needed at the receiver in order to get like a sensitive reception with very low error rates. Okay, so now I should introduce the concept of bit error rate before I try to explain anything else. So bit error rate, so it's essentially saying like when you have a stream of zeros and ones, like how often do you, at the receiver, flip that bit and then receive a 0 when you should be getting a 1 or vice versa, right? So that's basically what that's saying. So usually the standard for telecom is that you want really, really low bit error rates, not surprisingly. Usually something on the order of 10 to the minus 9 is considered to be reasonable. Of course, some applications may even want lower, but I think the idea usually is that there should be, if it's very important information, there should be some software overlay on top of that hardware to basically correct those rare errors. So this is very common, like with TCP/IP, for example, which is used to communicate like by fetching web pages, that if there is some sort of error, then you ask for a retransmit rather than just accepting incorrect information. But if it's something that's less critical, like you're just pinging some remote host, then you may not care if there is 1 bit flip, so you don't like try to resend. That's usually called UDP algorithm, right? So basically, anyway, the point is that bit error rates need to be below a certain threshold, or TCP will go crazy because everything has to be retransmitted, and then UDP becomes a useless algorithm, right? So in either case, you need to minimize it. So then this just looking at basically how important is the receiver sensitivity basically in order to achieve this very low bit error rate as a function of the bandwidth of some filter, okay? So I think what this is showing effectively is just that if you have a bandwidth that's maybe, factor of, let's see, 100 times wider than the optimum value. So that's basically this value here. Then your sensitivity needs to go up a little bit, and then so on. So basically, as you go to very high filter bandwidth ratios, like on the order of 1,000, then you need to have the highest sensitivities in order to maintain this low bit error rate that's desired. So that was my takeaway from this, and this also in the book. Now, of course, the final thing I should mention is about like all these like sources of noise that are happening in the system. So both from the Erbium-Doped fiber amplifier and the fiber itself, as well as your source and receiver, they can all kind of interact with each other. Okay. So then the question is, how do we treat all these different things that are happening at once? And so usually the best way is what's called the nonlinear Schrodinger equation. Okay, so basically the whole point of this is that we have different terms here, right? So basically dA/dZ is measuring like kind of propagation along the axis of the system. This second time derivative is basically a measure of the dispersion of the system. Gamma is a measure of the self and cross-phase modulation of the system. And then alpha is a measure of the loss. And so the nonlinear Schrodinger equation lets you combine the effects of loss, dispersion, frequency modulation, and propagation down the axis all into one equation. So you can basically track how everything is affecting everything else, right? And so the reason this can be important is you could have like a few things that are happening. Like you could have dispersion, you could have self-phase modulation, and maybe if they were just on their own, it wouldn't be too bad. But then if they start interacting, they can amplify one another, and then you can have like extremely high bit error rates. And so basically the way that you can treat this is basically when you have this sort of equation, then you can also add the noise by using this kind of term, where you would take your input signal, which of course has a gain associated with it as it goes through the EDFA, plus some sort of like time-dependent noise function. And of course you want this to be low, but like we said, it's not 0. And so then if you plug it into here, then you can track the effects of the dispersion and self-phase modulation and loss on both the signal itself as well as the noise, and then to see if the noise is actually being amplified to levels that will induce a huge amount of errors, right? Now, the catch with this equation is because it's nonlinear, there's not really a good analytical solution. So I'm not going to claim that there's one. Now, in my other class, and it was a 695 on numerical simulations, I did actually teach details of how to solve this kind of equation. But unfortunately, I can't say there's a simple analytical solution. But it's a good equation to kind of study these sort of problems.